Hi, I'm presenting our work towards robust classification model by counterfactual and invariant data generation. This is a joint work with Alex and Anna, and we are from University of Toronto. To motivate our work, we show a failure case of convolutional neural network that it cannot predict this image as cow when water is in the background. Instead, it is affected by the background and predicted as water. Similarly, a caption model described this image as grazing sheep, but there is no sheep in this image. In fact, it uses background to produce hallucinated foreground sheeps. And maybe a more alarming case happens in this pneumonia dataset that the CNN uses background's metal token instead of lungs to make predictions, discovered by saliency map visualization. This model will fail in a real hospital. Here we call these problems spurious correlations. We show that the factor U that affects both foreground and background, but only the foreground causes labels. But models might learn to use background to predict the labels, and which it will fail in datasets when background is totally different. To make a model more robust, we proposed a method we call counterfactual generation. So here is a shark jumping out of sea, and here we remove the shark within bounding box and impint it by a conditional generated model. Then we label this image as non-shark and let probability of shark goes to 0. So the idea is when the model faces this background, it should not predict this image as shark. Our second idea is to keep this foreground image shark, but we swap the backgrounds to another background from other classes. The idea is to make sure the model will output shark regardless of backgrounds. Here we list totally 9 different types of counterfactual and factual generations. We use different types of color, noise in painting, and also try different swapped backgrounds or even adversarial attack. And most of the literature focuses on directly regularizing the saliency map, for example input gradients, toward the bounding box. We use this as our baseline. Here we test our methods and saliency baselines on this semi-synthetic dataset called IN9. It creates a new test set called MixNext, which we show in the right that has different backgrounds of the next class. And we want to test if our models are still accurate in this setting. Here we show the accuracy of our models. X-axis shows how much data we use to train our models, and Y-axis is the test set accuracy. So here the higher the better. So our baselines are original, which is the blue one, and the saliency, which is the orange one. We show our methods counterfactual, the green one, and factual, the red one, all outperforms blue and orange curve. And our combination, the purple one, even outperforms baselines even more. Qualitatively, we show an example with carnivore foreground but insect backgrounds. We find our model successfully predicts this image as carnivore and dog, while original model predicts as insect and reptile, which is clearly affected by backgrounds. We further quantify how much our model is affected by backgrounds. So we swap the backgrounds of bird images with backgrounds of fish like sea, and we see how much probability of fish increases. Here, the lower the better. Both our counterfactual and factual have the least increase, and our combined method has even smaller increase compared to original or saliency method. Finally, we quantify how correlated between saliency on foregrounds and accuracy. In original test set, we see there's no correlation, which makes sense since you can just get high accuracy by just focusing on backgrounds alone. In MixNext, we find there's a stronger correlation, but we still find some outliers that have high saliency focus but low accuracy. We show more experiments in our paper. One of our limitations of our work is our methods can only deal with cases when spurious and causal features are separated. We make this assumption to allow us remove spuriousness without knowing what they are. We also require we have access to bounding box, which may be alleviated by pre-trained localization model. In this paper, we propose counterfactual and factual augmentations that outperforms both saliency and original in terms of accuracy when background is changed. We also find when combined with saliency methods, our methods improve even more. Finally, strong salience on foregrounds only correlates weakly with good accuracy. And thank you for your listening.